very much.
Okay, take it away.
Hi, mind if I stand here before the next session?
Oh, feel free. ICFP is fantastic, isn't it? Look at this amazing venue.
Yeah, it's a really great venue. I love it. Yeah.
And all these wonderful people you get to meet. I'm Eddie, by the way.
Oh, hi. What brings you to ICFP?
Equational reasoning, that's my thing.
Oh, nice T-shirt. Really like it.
I'm glad you like it. What's that? What about yours? Is that the bottom of a CPO?
Oh, no, it's not a bottom CPO. This is actually the symbol for an adjunction.
A what?
An adjunction. Well, an adjunction is, well, it's just a natural isomorphism between the Hom sets of two categories where the left adjoint x on the source of the objects in one of the Hom sets and the right adjoint x on the target of the other. What's the problem?
Can you give me an example?
Oh, sure, yeah. Would you pass me that napkin, please? Thanks. So I guess that you can think of an adjunction as essentially being something along the lines of this, where if you have something like diagonal and product, then it establishes that if you have two functions f and g that share a common target, common source a, then that's the same as a single function h that goes to b cross c.
Okay, but now that looks pretty trivial. What's all the fuss about?
Oh, okay. Let me try something else. So think about the Galois connection between the reals and the integers. So there should be an obvious way to take any integer and then turn that into a real number. You can just think of that as adding a 0.00 to the end of it. That's the injection. And there's another way of doing this, which is to take a real number and then just remove all of the things after the decimal point, and that goes the other way, and that's going to be something like floor. And if you look at the bottom of the napkin, then you'll see that if you have an injection of some n that's less than or equal to x, then that's the same as saying that n is less than or equal to the floor of x.
Oh, that's very interesting. I mean, I can see how you can use that. You can you can define division on integers in terms of this floor thing, right? So you can take the two integers, you can inject them into the reals, you can do a real division, and then take the floor of that. And you get the equational properties of div come out of that equivalence you had. So you can turn a complicated problem about reasoning about div on integers into a much simpler problem, reasoning about multiplications on the real numbers.
Exactly. That's the insight that makes me really excited about adjunctions, is that it allows you to take a problem from one domain where you might be finding things difficult to the operations that you have at hand into another domain where it's much easier to solve. So with the Galois connection that we saw earlier on, it's just much easier to work with multiplication over the real numbers rather than tricky division over integers. Yeah.
Yeah, so actually that reminds me of the previous talk to do with homomorphisms over commutative monoids, for example.
Right.
Consider these two homomorphisms, the map over a bag. So map takes a function f and a bag of elements x, and for each a in x it gives you f of a. And filter takes a predicate p and a bag x, and for each of the a's that satisfy p, you get the result. So it's the a's drawn from x where p holds of a. And they're both bag homomorphisms. And moreover, when you compose them, you get a bag homomorphism. And the composition has this equational property. These two operators commute. Filter p after map f is map f after filter p after f. And in order to prove this, because they're both the left-hand side and the right-hand side are bag homomorphisms to the same commutative monoid, it suffices to complete the proof to think only about the singletons. So all the real work is in the action on singletons. And that's much easier to deal with because there's no recursion there.
All right, yeah, that makes sense, because I guess there's probably an adjunction hiding here as well between commutative monoid homomorphisms and their actions on sets.
But now I'm confused. I mean, you said that adjunctions were about pairs of functions, and then you said adjunctions were about division, and now you said adjunctions are about bag homomorphisms. What's going on?
Ah, right. Okay, so let me give you the more general picture. So an adjunction is just a piece of category theory that says that you have two functors, L and R, connected together between categories C and D. And really the trick is to think of the C on the left-hand side as being arrows where the source has been modified by some L, so that's LA to B. And they're in a one-to-one correspondence with arrows on the right-hand side where you have D, in D, where you have A to RB. And the thing to remember here is that because we're in categories, the notion of arrow means that you can overload that and do different things with it. So, for instance, the first example I had on the left-hand side, pairs of arrows rather than single arrows sharing a common source, that's the diagonal over A, going into the product B cross C. And in the second example, I showed you about injections and how on the left-hand side, and how the arrows here are all comparisons, so less than or equal to.
Yes.
And on the left we have an injection, and on the right we have a floor.
Yep.
Now, in your case, when we're thinking about bags, we're dealing with a different adjunction, which is between that connect the two categories, one for commutative monoids and the other one for sets. And what the adjunction tells you is that if you're going from bags of A on the left-hand side into some commutative monoid B, then that's the same as having functions from A to B. And the reason that is that on the left-hand side, the free functor applied to A is precisely bags, and on the right-hand side, the B comes out of forgetting all of the additional commutative monoid shapes. So this is exactly where you get those properties from, and that's why your problem seems to work. But what made you think about commutative monoid homomorphisms in the first place?
Well, that's very interesting. I've been looking at query transformations, so database queries. Think of them as bags of tuples of values. Bags because you want to be able to do aggregations of them. You want to be able to sum a bag of things or count the elements of a bag of things or even find the product of a bag of things. Those aggregations are all bag homomorphisms. They're all homomorphisms of commutative monoids.
Oh, that's really interesting. So how would you do things like selections and projections?
Well, so I'm glad you asked. So they are commutative monoid homomorphisms too. So what the database people call selection, sigma p, they write, is just a filter, and that's a bag homomorphism. And what they call projection, to take a table and keep only some of the columns of the table, is just a map with a function that does the same thing for each tuple. So they're bag homomorphisms, and the equational properties, these things have nice equational properties, like the composition of two projections is a projection, the composition of two selections is a selection, and there's this commuting property between selections and projections. So those equivalences just come out of the laws of aggregations, which are the laws of commutative bag homomorphisms, commutative monoid homomorphisms.
Well, that's fascinating, because these are actually optimization principles that you could use in your database queries, and they all come from the fusion properties from the adjunction. So because we're going from an initial object, that's bags, into every other place, there's always a unique arrow that goes from bag to those things, and so those unique arrows induce these fusion properties that we're looking at.
Right.
That's absolutely fascinating. But it's one thing to think about selections and projections, but we all know that databases are about selections, projections, and equijoins. Let me think about how you might do that using your bag notation. I suppose you might write something like this, using a bag comprehension, where you're saying that you've got two tables, x and y, and they're joined together on the f and g. And I suppose you would say something like, here are all the a's drawn from x, here are all the b's drawn from y, and then we equate them when fa equals g of b. But I don't like this formulation because it's really inefficient. Look at all the huge Cartesian product that I'm producing. This generates a really massive intermediate step. That doesn't seem very good at all.
Yes, so it produces a lot of data, most of which you throw away. So that is indeed a specification of equijoin, but it's not a very good implementation of it. So instead, you want to do something like indexing. So you can take your table X and index it on the F attribute, and then you'll have a mapping from keys to little bags for each key, those elements of table X that have that value for the key. And you can do the same with table Y. You can index on its G attribute, And presumably, f of A and g of B of the same type. So now you have two index tables with a common index type. And you can merge those two tables to make one table from keys to pairs of bags of values, and then you just do a little Cartesian product on those little bags. So you take the little bag of A's and the little bag of B's that have a common key value, and all of those are proper values. All of those are things you want to preserve in the result. There's no junk, and so you just then go and flatten this index table.
Wow, that's a pretty fancy way of calculating this. I guess it's a lot more efficient, but it's not at all clear to me that these two things are equivalent.
Right. So there is a job of work to prove that they are equivalent, but it's not too difficult to do. And again, it uses the equational properties of bags. It's quite a nice proof. But yours, it's good that there are both of these things because there's an efficient implementation that runs nicely, but there's you have a nice clean specification that is actually more convenient for equational reasoning with. So you can, here's a proof that equijoin is commutative up to fiddling with the tuples.
Blimey, how did you write so quickly and so neatly? That's beautiful.
A beautiful proof deserves beautiful handwriting, don't you think?
Well, this is all very nice, but I can't imagine programmers actually want to use this. They're used to things like SQL syntax, where they have selects and that sort of thing. That's not at all like what we're writing
Right.
about.
So, indeed. So in relational database world, they talk about relational algebra and relational calculus, and the algebra is things like selection and projection and join and merge and index by. And the calculus is the SQL notation, where you talk about typical elements of the result. And we have something similar in functional programming, right? So you have you can write maps and filters, map square of the even elements of X. You can write it in algebra style, or you can use a comprehension, and you can write it in calculus style. So it's the squares of those A's drawn from X where A is even.
Oh, I see what you mean. So that's actually quite similar to what I was writing as my specification, where here instead we have a bag comprehension where we're saying that we want to do a comprehension over a slightly different data structure. And I guess that kind of makes sense because I'm sure you realize that every time you have a comprehension, there's also a monad lying around in the background. And the cool thing about adjunctions is also that every adjunction gives rise to monad. And this is exactly the monad of bags that we're looking at. And so it gives rise to the notation that we need for this too. Very neat.
Yes, yes. And it's even neater.
Go ahead.
It's even neater because you can even do the fancy equijoin in this way. There were a couple of really neat papers from the Haskell Symposium over the past few years. One by Simon Peyton-Jones and Phil Wadler showing how to generalize list comprehensions so that you have a kind of grouping and a kind of zipping operation there. And then later by George Georgitsa and co. Showing how to do that not just for lists, but for other monads too. So you can write the fancy equijoin, the efficient equijoin, in the calculus style as well as in the algebra style. So here's the syntax, and you'll see there are two vertical bars in that comprehension. So it's doing two two sub-comprehensions in parallel. So you take the A's from table X and group them by their F attribute using this index by operator. And you take the B's from table Y and group them by their G attribute. And do those in parallel. And the in parallel thing is the merging of those tables. And then you just do the Cartesian product for each little sub-bag and flatten the results as before.
I can see that's a really nice story for writing my query down in a sort of more programmery way, but I'm still quite confused. I mean, looks like we're talking about monads, but it's not very clear to me that every monad has these sorts of group bys. Isn't there something fishy going on there?
Well, so that is interesting, because I bet this doesn't work for the state monad, for example.
Exactly.
So, and what monads does it work for, and what are the properties of grouping and zipping? No,
Sounds like something for next year's ICFP.
Yeah, maybe that's my next paper. Yeah,
Right.
Yeah, good idea. But there is something fishy going on here, consider this return for the table monad. So we had tables which were functions from keys to bags of values. Bag is a monad. Functions from keys. Key arrow is like a monad. It's a reader monad, and those monads compose. And this is the return of that monad. So it just ignores the key. So for every key, k, you just get the same singleton bag with one element in.
I don't think there's any fish here at all. There's nothing fish here at all. This is just an ordinary monad, isn't it?
Well, it is just an ordinary monad, but I want to do aggregations of these tables as well. I want to be able to count them and sum them and find products of them. And for that to work, it better be a finite table. And this is absolutely not a finite table. When the key type is infinite, like the integers, this has got infinitely many a's in, so count that.
Oh, right, that's completely the wrong monad. You can't use this one for finite things at all.
Right, so what I want to do is use finite maps. And I know how to do that. I mean, you can say that a pointed type is a type with a special distinguished value, and a finite map from keys to values is one that gives you that default value for all but finitely many keys. And bags are a pointed type with the empty bag as the distinguished value, and so a finite map there is one that gives you the empty bag for all but finitely many keys. But this doesn't seem to be a monad anymore. This is not, I can't make the return for the monad.
I guess we're kind of stuck. But hang on a minute, that kind of reminds me. I was just reading this paper. Let me get it out. So, so this is a paper by Fuji, Katsumoto, and Méliès about graded monads. And I think they've got exactly the kind of thing that we need to solve this. So the idea with the graded monad is essentially that it's the same as a monad, but rather than having an ordinary functor, it's a functor indexed by the elements of a monoid. So let me give you an example of this. So this is how you'd formulate monads that are indexed by elements instead. So the return, that's the eta, is going to go from an A to not T of A, but rather T of epsilon A, where epsilon is the unit of that monoid. And for the multiplication, or the join of the monad itself, mu, we go from T of M of T of N of A to T of M cross N of A. In other words, you use the multiplication of the monoid to combine these two things together. So these are index functors instead of ordinary ones. So perhaps as an example of this, you might think about vectors. So a vector of size 1 would come as the result of just the ordinary return that goes from A to T, to vectors of size 1 of A. And so 1 is the unit of the monoid of multiplication, and you see that coming up again in the multiplication of the monad. So for mu, if you have vectors of vectors, so you've got a vector of size m of vectors of size n, then that can be turned into a vector of size m by n. This is essentially the concatenation of these vectors together. I suspect that for your tables, it'll look something like this, where instead of going, where the indices now are going to be over the kinds of keys that we have. So we either have empty keys, which is going to be what the return gives you, so from an A to a table of empty keys of A. And for the joining together of tables, when you've got nested tables, a table of indexed by K of tables of A's indexed by K prime, then you can just combine these two keys together using concatenation. So this is the monoid of just ordinary strings and lists.
All right, so I see these are the column headers in my tables, and there's empty tables with no columns, and you concatenate the columns.
Exactly.
Cool. So let me see if I got that right. All my favorite equations, you say they just come from adjunctions, and bags and monads, that's cool. I can also fit in these index tables, and I can do equijoin, and that also comes from adjunctions. I guess these graded monad thingies have adjunctions behind them. And the graded monads also explain how to do finiteness. Also let me restore the ability to do aggregations of these tables.
That sums up really well. I think I finally understand how databases work.
Great, thank you. And now I know where all my favorite equations come from.
I think the next session's about to start.
Okay,
cheerio.
Right, we better go.
Thank you very much. So the first question here is, can you apply your work as a practical recipe for building optimizing query planners?
Do you want to go first?
Okay.
That's an ambition, so I would hope so, but we haven't done that yet. I mean, it helps us to understand what's going on, and I'm a bit suspicious as to whether we can actually do anything that the database people don't already know. So I'm not proposing to make a new database company and sell us all, but I think you could reconstruct the optimizing compilers.
We've not spent any time thinking about how you would do statistics over the kind of queries that you've done and how you go into tables and work out which are expensive, which are cheap, and how to sort of move these things around. The point of this paper really is to think about where the different optimization laws actually come from and where the structured databases come from. And it sort of all comes into adjoints, but we've not actually done the kind of nitty-gritty of making this a real practical system.
So you haven't discovered any new optimizations from this?
No, it's the strength of the paper that it explains the existing ones, I say.
Okay. Are finite maps a free extension?
Don't know. Sorry, I don't know the answer to the question.
That's a question for Andy.
Okay. Oh, right, we have a very different flavor of question here, which is, well, how did you choose to present the paper in this way? And what are the advantages or disadvantages do you think it has over a traditional conference presentation?
Well, I'll let the audience talk about the advantages or disadvantages, I think. We both like presenting at ICFP, and we both wanted to present, and rather than have a fight about it, we shared it.
And also, I think some of the content might have been just a dry category theory. Like, here's another equation, here's another definition. I thought this was sort of a fun, playful way to do it. Yeah.
Okay. Do graded monads come from some kind of graded adjunction?
Yeah, that's exactly right. So the theory of graded monads that does come from another theory of adjunctions, there's just another. That's exactly what the paper was that we pulled out and said, here's the missing solution. They precisely go through that adjunction and show how it works out.
So that comes from the formal theory of monads by Ross Street in 1972. It's old stuff.
Okay, good. Thank you very much.